Okay, I think we should get started. Thank you for joining us today for the first Directors Seminar of the year. I'm thrilled to be here today to join you in this. I am Nadia Mason, the new Director of the Beckman Institute. And it's great for all of us to come together. Thanks also to those of you on Zoom for joining us as well. I'm especially pleased to be able to start my first day as director in this event, which is all about coming together, which is about sharing a meal, which is one of Jack's big reasons for coming together, which I really appreciate, and for learning more about the diverse research which is happening at the Beckman Institute. And if you'd like to stick around after the seminar to say hi, I'd be really happy to meet you and say hi to many of you if you're willing to come up to me and say that. And also, after the talk, I'd also like you to join me at 3:15 in the East Atrium for an all Beckman photo. 3:15 East Atrium, all Beckman. Put on your swag if you have some, otherwise just come as you are. It's for this year's annual report. The theme is Beckman's Bright Future, and I'm sure you don't need any more incentive, but if you do need more incentive, there will also be donuts. So come for the donuts, stay for the photo. I hope to see all of you there. Okay, so I'm especially pleased to introduce today's speaker. This is Randy Ewald from the professor and Kreitzer Faculty Scholar in the Department of Mechanical Science and Engineering. He's also part-time faculty in the Autonomous Materials Systems Group here at Beckman and an affiliate member of the Materials Research Laboratory. So Randy received his bachelor's degree in mechanical engineering from Iowa State University and completed his master's degree and PhD in mechanical engineering at MIT. He conducted his postdoctoral research at the University of Minnesota, and in 2018, he served as guest professor at the Swiss Federal Institute of Technology in Zurich. So do you speak German or French?
Nicht.
So his researching areas include soft matter, fluid mechanics, and rheology, which is the study of how matter flows. In today's presentation, we'll discuss the rheological properties and principles of non-Newtonian fluids, exploring how we can use these complex materials to achieve diverse outcomes in engineering and design. So if any of you have ever played with, say, cornstarch mixtures at engineering open house, you know how fun and engaging non-Newtonian fluids can be. So his talk is entitled Squishy Materials Toolbox, Complex Fluids, and I look forward to hearing more about this. Thank you.
Great, thank you very much. Just check this is muted again. Yes, all right, we're good. Thanks for showing up. I'm sure the free lunch helps, but I'm so glad to see you here. So as introduced, I sit in the Department of Mechanical Science and Engineering, and I have an office. You'll find me at Beckman on the 3rd floor around the tower room area, where I interact with the AMS group and the molecular design and engineering group led by Charles Schroeder here. And it's a pleasure to be with you. So squishy materials, let me just say, what do I mean by squishy materials? I mean, things that are like fluid, but they're kind of solid, or they're solid, but they're really soft and kind of fluid, or things in between. And you've all seen these, as mentioned too. You've seen cornstarch and water. It's kind of peculiar. I've even brought some demos. We'll see if we can pass these around, but you can find these things from your local physical therapist, actually, that has a range of these putties to help you strengthen, for example, your hands after an injury or surgery. They come in a range of viscoelastic properties. And so you can buy easily viscoelastic materials for your own demonstrations. And you see this in everyday things like aloe gel. I've got a pretty pasty white complexion. And so when I get burned in the summer, this is sort of the next go-to thing to ease my sunburn. But it's non-Newtonian, maybe because they want it to be, maybe because that's just how the chemical formulation comes together to be complex. You can exploit that either way. And one way to see that it's non-Newtonian, this should be a video here. This is water in the foreground and something like this aloe gel in the background. And you see both of them are flowable like a fluid. You can squeeze them out of the syringe, but the gel in the back doesn't always flow. Really only flows if you push on it hard enough. We would be a little bit more precise and say there's some critical stress above which the fluid flows, below which it acts like a solid. You see that in the jar because you see bubbles that are trapped. They don't rise to the top. So those bubbles have a buoyant stress. See some students from my ME 310 undergraduate fluid mechanics course in here. We'll talk about buoyancy in that class. The buoyant force is not enough to push through this gel. You've probably seen this before, but I have to pass it around as a demo because then you can really feel the rheology. In case you're interested, you're welcome to take a pump of the aloe gel as it goes around. So that's just one way to be non-Newtonian or squishy and complicated. Let me explain this subtitle here. There are many ways to be squishy. You can be soft and squishy, like human skin is soft and squishy. People call that a soft material. Elastomers, rubber materials are also soft and squishy, but today's talk will really focus on the fluid side and how those can be complicated. Before I get too far into any technical detail, I want to make sure that I acknowledge the recent group photo here. Many of the folks in the group, thanks for showing up. Appreciate that. You know what we're doing in the group and you show up anyway to see how I talk about it in front of a crowd. Thanks for being here. And I want to thank Nadia for the introduction and being willing to accept the fact that I had already been assigned to give a director's seminar even before she accepted the position. And thank Jeff Moore, who's with us. I thought you were retired and taking a 60-day study break. Actually, I'm honored. I'll consider this part of your study break. This is great. Thanks, Jeff, for the invitation and for being here also. And these groups, as I mentioned, and many collaborators, Beckman and beyond, and a few funding sources that have helped us to think about how to design things based on these complicated behaviors. Right, so there's more than one way to be complicated. There are 4 of them that are really important. So I was passing around that alogel and demonstrating the video. That's one way. We call that shear thinning. And an extreme case of that is the alogel, which is so shear thinning, it really acts like a solid at low stress. We call that a yield stress fluid. So if you want to pull out a few bits of lingo, in case you haven't bumped into this before, that's something to note. Yield stress fluid. The other most common one that you've seen is this. This is something like silly putty. It's the physical therapy aids that I had mentioned. I'll pass a couple of these around too. You know that this is weird because it takes the shape of its container. It's clearly a fluid, and that's shown in the picture because it flows under gravity, drips through that hole. But at short times, it bounces like an elastic solid. And again, going back to how we teach things in our undergraduate curriculum, we don't really teach about fluids that are both, or materials that are fluid and solid at the same time in the undergraduate curriculum. We like to divide and conquer in the sciences and in engineering. So we have a course on fluid mechanics, of course, a separate course on solid mechanics, and they don't really get combined until more advanced curricula, usually at the graduate level. So I teach a course on rheology. Courses that have the words viscoelasticity in them start to combine these ideas as well. And so maybe I'll pass around a couple of these. Here's this blue putty. You squeeze it in your hand. This is the highest resistance. Your physical therapist wants you to achieve this level of strength in your hand after your surgery or your hand injury. And it comes in many different grades. Pass this one around first. Maybe, I'm not going to pass around the container, but I'll just warn you, try to not drop it on the floor because it picks up dust quite easily. And I don't want to be responsible for this also staining the carpet or like getting into the carpet. But I think it's slow enough. You don't have to worry about it. This will probably warm up as it gets passed around. And these properties are, of course, temperature dependent. When it's warmer, things are easy to move. Let me contrast the blue with as close as I can get to orange in this collection of fluids. And this is labeled as soft. What do they really mean by soft? Is this like elasticity? Is it viscosity? Is it something else in between? The marketers don't really care what it is. They just call it soft. And the physical therapists are fine with that. But you'll definitely feel it's very different. What you're actually feeling, though, as this goes around, you're really feeling the flow viscosity, the resistance to flow. It's harder to feel the elasticity, but you might try it by twisting and then letting go and seeing if it recoils back. That's the evidence that there's elasticity. Or if you're really, if you have a hard surface, you can try to bounce it and see that if you're maybe hearing this through the mic, it definitely has elasticity. Just for fun, I'll pass this around too. So it should feel a little softer. Those are the 2 main ways to be non-Newtonian. And you've already seen examples where it's maybe useful. You know, if this was really just a viscous fluid that had that same viscosity, you'd never be able to handle it. It would just be a goopy mess. But because it has elasticity, it actually makes it workable. This too, it's good that this is a gel, just like our gel to hand sanitizers. They kind of stay where you put them rather than flowing all over with a very thin viscosity. And you can do a lot of other interesting things, and I'll mention that in the future slides here. There are 2 other ways to be non-Newtonian. One of them is to have a high extensional viscosity, so resistance to extensional deformation. It's used a lot in polymer processing and making things. And then rod climbing, which is usually just a pain. When you stir some liquids, instead of flowing to the outside of the container, they wrap themselves around that spindle and climb up. Depending on your cake batter formulation, you may be able to see this in your KitchenAid mixer if there's enough elasticity from the gluten that's in the flour. Gluten's a polymeric material. It forms a network, and it's that elasticity that's helping it to wrap around. Again, usually that's a pain in an industrial setting. There are problems that have happened because of each of these things, but if you're clever, you can do something useful with it. Next slides are just some videos demonstrating the same thing. So it bounces at short times, it flows at long times. We use the word viscoelastic to capture each of those effects. Here is an alternate take for the shear thinning. So I think I'll skip over this because you saw that other video a couple of times. Let me show the extensional thickening one. This is water on the left, small molecules, only water, salts, of course, coming out of the tap maybe. On the right is mostly water, but with a high molecular weight polymer, and that's what's making these properties behave very weird. So it's molecules that are huge, millions of molecular weights. We've also increased the viscosity here by adding in glycerol that slows some things down, but you see how it's forming this film, and you can imagine why this may be so useful. If you want to make very thin or very small things, you can stretch out a liquid, get it to solidify in that state, and you can make thin films or thin fibers with this sort of property. And finally, the rod climbing phenomena is contrasted here with water on the left and something non-Newtonian on the right, but really specifically a polymeric solution. So now you can start looking for these things in your everyday life. And if you're on a campus like this, close to a wonderful library like the University of Illinois, you can find textbooks that have been around for a few decades now that write about how to think about the physics and the mechanics of the fluid mechanics of how these things will flow. You'll find another category of textbooks that think about the molecular picture. Where do these properties come from? But it makes it a very big interdisciplinary field. Beckman ends up being a great place to think about these questions because you end up connecting with people who think or care more about the molecular side, or maybe who care more about the flow and the deformation side of things. I haven't yet found a way to connect with the psychologists that are here, and I would still love to. Maybe the putties are a way to do it. Like, what are you really perceiving when you squeeze or interact with these things? Might be a fun invitation in case you're so inclined to interact with me on that. So there's the landscape. Here's how I come into this. This equation is just F equals ma, Newton's second law of motion. Many of us see that when we take a physics class, maybe in high school or college, but it's more complicated because things are vectors. You see these underbars, that's my notation for a vector. You see time derivatives, and you see stress here has 2 underbars. This is because stress is a tensor. Stress is what you're applying onto the material and what gets generated inside of that material. And if you're from the mechanics world, this is maybe very comfortable. You see this in undergraduate solid mechanics, many different ways to apply a stress. You have to do the bookkeeping. And in this equation for how fluids or any continua will move and flow, that's where our complexity really comes in. I have this up in case you're coming from a fluid mechanics backgrounds. Fluid mechanicians like to think about the complexity of the velocity fields. You may know people, or you may be in the audience, if you think about turbulence, complicated flow fields, a lot of complexity that's worth considering on this side of the equation. In our world of non-Newtonian fluids, we often prefer to think about more simple velocity fields, and we think a lot more about designing, in our lab's case, how complicated that stress tensor can be. And we call this constitutive behavior or rheology. That's what I mean by complex fluid. I mean complicated compared to a Newtonian assumption. What do I mean by design? I love this word. Dina was here. I don't know if Dina's still here in the back. Oh, that's great. This word design gets used in Beckman a lot. I've used this word design for some time, and it's been really fun to check in with different people groups around campus, around the country, around the world, of how people interpret this word design. So for example, I have friends who are graphic designers, and they define the word design to certainly be a creative process. You're making something that didn't exist before. Engineers who use the word design often think much more quantitatively, like I'm optimizing something. That very quickly comes to mind when people talk about design. Of course, it means all of these things and maybe more as you look across the landscape, but I'll stick with this general definition. You're either creating something, fashioning something, executing, or even constructing according to a plan, or even if you don't make it, but you conceive it and you plan it out in the mind, you may be a designer. Maybe you're the architect that comes up with the design. You don't have to build the thing, and you're still doing design. And so you'll see that flavor here where we think theoretically about what we can do, and we also think experimentally about actually making these things. So Isaac Newton his name is all over everything. Like this whole equation you could say is Newton's law of motion, F equals ma. His law for how viscous fluids like honey and water respond to stresses are called Newton's law of viscosity. You just can't get away from it. But you can actually get away from Newton by violating his laws, and it's harder to violate this overall law, and it's easier to violate his law for the stress tensor. And that's how, when people use the phrase non-Newtonian, that's what they mean. It's anything that's not obeying Newton's law of viscosity. And as soon as you do that, you get this explosion of possibilities. I've shown you those 4 key phenomena, but there are even more beyond that. Okay, so is there anything useful here? I think for many decades, this field was really driven by people just needing to deal with the complexities, not that they wanted non-Newtonian, but it just was non-Newtonian. So for example, injection molding doesn't have to be non-Newtonian to make injection molded parts, but when you melt a polymer, it is non-Newtonian, and so you need the math and physics to figure that out. And then as you start getting clever, you might say, actually, being non-Newtonian can be good because I can actually create other shapes if I can do that. So with apologies to XKCD, here's one way to frame some of our recent thinking. You know, if you have an engineering problem and you want to solve that problem, you might ask, would non-Newtonian behavior actually help me to do that? I'll show you examples where it does help, but whether it helps or not, if it does help, the 2 other questions to ask is, which of those properties do I actually want? Do I want that viscoelastic thing? Do I want the shear thinning thing? There are all of these things in the toolbox. And if I know what I want, how do I get it? And this last question gets down to the molecular design or molecular thinking about how to make these materials. So here's a reminder of these 4 key phenomena as one way to organize one's thinking about what different things might be useful. This is taken from a paper that Chai Sengao and I wrote together. Chai is a Beckman postdoc fellow. I think I saw him in the audience. Hey, Chai, thanks for being here. Again, you know things in this talk, and yet you come anyway. I thank you for that. And this is great. So Beckman fellows have such great opportunities here. And one of them was that Chai got to think about a very high level review article with me that was just published in the annual review of fluid mechanics, after which some of the content here is inspired. So thank you very much to Beckman for making that possible. So here's ways to be useful. No matter which way you're trying to make something complicated, you have to think about the molecular structures. I give you an incomplete list of ways to make your structure complicated. Ooh, did these self-diffuse into each other yet? Oh, so close. Yeah. Thank you. They still feel different to me. They're both warmer for sure. Yeah. I'm feeling your energy. All right. Right. So in the world of material science, you may find people who like to think about polymeric materials, and they focus on the physics of that. You may find people who think about colloidal systems, so particles that are small enough to be kicked around by Brownian motion and thermal motion. You add in attractive interactions, you can make them stick together, and that gives you these properties at the much larger length scale. There are also things like emulsions. So if you've anybody made mayonnaise by hand, made it themselves? I see a couple hands. Now people are willing to admit. It's a bit of a tricky process because you can wreck this, but if you drip in the oil slowly enough, as you break that into droplets, you start off with something that looks like it's dilute. And as you add more and more of that oil droplet and you keep those in the dispersed phase, you make sure it doesn't invert, you get something where all of those oil droplets are very crowded in the system. You know, mayonnaise is like, I saw the packets of mayonnaise. It's like 80% by volume oil is pretty much what it's like a way to solidify the oil and get it into your system. But this is what it looks like at the microstructural perspective. You know, this droplet size may be on the order of like 10 to 100 microns, whereas this polymer coil size may be a few tens of nanometers. And so it covers a range of scales, and we end up thinking hierarchically about where the properties come from. How can we be useful? Let me just show a couple of pictures of achieving these diverse objectives. So for example, there's a whole field where people want to make injectable hydrogels so that when they inject something into a biological system like the human body, things stay in place. And so you want it to act like a solid under those conditions, but you still want to flow through the syringe. Rheology is a great tool to make that happen. So how can are non-Newtonian properties useful? Yes. What do you want? You don't want the viscoelasticity. You don't care about the bounciness. You just want the shear thin. And so there's kind of this down selection of how to get it. There are many microstructures. Usually polymers is what people are using to get that effect. In energy, so through the Beckman, we've gotten support through a Department of Energy effort called the Joint Center for Energy Storage Research. They care about batteries at large scales. And one way to do that is to have liquid-based storage of electrochemical energy. And when you make those liquids out of things like polymers or colloids or even smaller molecules, things get complicated. You have to think about the viscosity or other properties that result. Sometimes it's good and sometimes it's not good to have those fluids be be solid-like in the flow. We've had projects that are related to fire suppression. So it turns out if you make water into a gel, maybe something kind of like the Alogel, you can still load up a 500-gallon tank in a fire truck. It'll still flow through the pump. It'll flow through the hose. It'll spray out like water. But then when it hits and impacts, it will stick and form a layer. And what the companies will claim is that suffocates the fire, and they'll sell the product to people to use it. Of course, the science of what's really going on there is still being understood, because not much work has gone into understanding the physics of complicated fluids impacting and splattering and setting up a coating. And that's motivated some of our studies there. And you can also do things like be inspired by nature and make soft robots that are soft and squishy. This is an example of how snails and slugs actually crawl around. There's a thin layer of fluid that exists underneath of them. Here's a model of a robot that we built to walk around like a snail does. And if you make that fluid non-Newtonian, you could use it like an adhesive that lets you shimmy up the wall. This is not working like a gecko works. Geckos don't need the liquid, but the snails need the liquid, and that's the trail you see left behind. And it works because it's non-Newtonian. Here's one specific example that connects back to Beckman and Yilin Wang, who's a current PhD student in the group, collaborating with people here at Beckman, looking at the viscosity and other flow properties of these fluids that you put inside of a flow battery. And as you add in more stuff into those liquids, it's good because the stuff you're adding in allows you to have higher energy density. Some molecules are electrochemically active. The more you put in there, the more energy it can store. As you do that, though, unfortunately, the viscosity goes up and then starts going up even more rapidly until it's much more viscous than you'd want it to be. And around the time that's happening, the conductivity of your system, which you want to be at least above a baseline, starts going down again. You need the conductivity, of course, to conduct the electricity and store the energy. And so there's some interesting design trade-off here of how much you can increase the energy density, but how high the viscosity is getting and how the conductivity starts dropping again, even with the Newtonian response. And so Yilin has looked into problems like this from this kind of design perspective of seeing the viscosity going up, rationalizing why the conductivity comes back down again, and relating it back to molecular structures that are in the fluid. So this gets to design questions, but on this slide, I like that this points out, we may be motivated by design, but sometimes it's hard in the scientific literature to publish a design paper because people are trained to review a scientific article from a science analysis perspective. You know, given a system, tell me what's going to happen with it, rather than the design perspective flips this around. I think I see Dina nodding in the back. The design perspective, you know, it doesn't care about a single solution. It needs to first consider many possible solutions and then down select and see what's actually the right result. So there's kind of a tension between design thinking and the scientific literature right now in the course of human history. Maybe that will change going forward. There are areas of people who talk about design science. There's a lot of great activity there, both on the engineering side and outside of engineering. So there are many ways to be useful. The 4-panel Venn diagram here is indicating each of those 4 key phenomena. You can think back to the videos or the demos passed around. This is the shear thinning area. This is the viscoelastic extensional thickening and normal stress differences. And we had fun finding examples where people have done something useful or interesting, all the way from adhesives to really clever things where in small scale flow channels, you can get things to focus at the center just by making the fluid a little bit non-Newtonian. This is really neat, actually, with a colleague in mechanical science and engineering. They needed particles to be at the center of a channel, and this is really hard to do that in some other way, or they're moving around their optics, depending on where things were, and you put in just a little sprinkle of polymer, and it drives things to the center because of really cool physics that are coming from that N1 effect. The cake batter up the KitchenAid mixer effect is happening inside of here, although it's not rotating, it doesn't need to be, but that's driving particles to the center, and then it's much faster to do things like optically image or probe them in other ways. You don't need these other effects, though. Again, this is just a reminder, you want to do something useful, you don't need everything, you just need to know how to select the right thing, and our review article is helping to map that out. Maybe the most useful thing, though, is the Alogel. So this property of having a yield stress is used, we've found, more often than anything else. It's used in direct ink write printing. I see several people in the audience who have experience with extrusion-based manufacturing. Maybe just a quick raise of hands to see where you may be. Who's done anything related to extrusion-based anything, but especially manufacturing? So people in the audience here, there are many ways to extrude something and get it to solidify. So you could do free-form printing. One of them is to make your fluid non-Newtonian, like a yield stress fluid. as you saw with the demo video, and as you see here, the material flows through the nozzle. When it comes out, it's acting like a solid. The stresses from surface tension or from gravity aren't big enough to make this collapse down, and it can self-support. This is at a small scale, so this diameter of the tip is about 200 micrometers. We can print even smaller in a collaborative project with Sam Tofik. I think I saw Sam because he raised his hand. Thanks for identifying. We're thinking about the rheology of these printing inks in different scenarios, but trying to get down to much smaller sizes. We've gotten down to on the order of tens of microns, plus or minus. We got close with this project. We're getting even better with some other tricks in our project with Sam. What else can you do? Where else might you see this? You see this with adhesives and coatings. This video on the left is a green fluid that's stuck between two plates. The top plate gets lifted off, and you happen to see this really cool physics fingering pattern that remains because of the physics here. You'll see it even in pharmaceuticals. So we had a project where pharmaceutical sprays, nasal sprays, wanted to have this property so it sticks and stays where it deposits. You see it in foods. We've had some projects supported by the food industry. I always show this picture, but this is so old now, it's an antique. Has anybody ever seen this drink called Orbitz? Okay, so I had to buy these. I have a few of these just as demonstration in my lab, and I had to go on eBay and basically find them as antiques because it's not sold anymore as a product. I think the US market just wasn't friendly to this, this type of drink. These suspended red spheres never sediment and they never float to the top because the clear liquid has an almost imperceptible yield stress. And so it's pourable under gravitational stresses, but under the much lower stresses on the order of, if you're in the business, like less than 1 Pascal, more like 0.04 pascals, which is unimaginably low for you to feel. But these particles feel it because of their density difference. They neither rise nor fall. They're just stuck in there, and yet the fluid is still flowable because the gravitational stresses are much bigger. That scales like rho GH, and so you easily get above several pascals just with the small length scales even at the top. We've had fun with other things too. Maybe in the fun direction, you can also do magic tricks based on rheology. And I'm not sure if I should even show this to you because it may violate some agreements with the Magicians Union. But you can actually buy these things. So the one on the left is something called Mystic Smoke. Kind of fun. You just buy it in a little tiny tube, squeeze a little bit on your fingers, and it's intended to make it look like smoke is generated from your fingertips. So that's what we see on the left. It turns out this works because of the non-Newtonian properties. One, you put it on your fingers and it doesn't flow away. So that's good. And you can make it flow when you want it to. It has high extensional thickening, which causes these fibers to form rather than breaking into droplets. And then the fibers stay, which is a type of yield stress behavior. It's acting again like a solid. So it's kind of going through these different points in the process, exploiting the non-Newtonian behavior. This other material is called Octopalm. And you can see that RF, former student, now faculty at Singapore Institute of Technology, is using this as a way to do this disappearing coin trick. And then he reveals the trick because it's sticking to the back of his hand. I should have checked in. Are there any magicians in the audience? All right, I think I'm safe then. That's great. So this has been a fun tour of things. I've like not really gone into any technical depth in any of these. Maybe you prefer that, or maybe you'd like some technical depth. I'd like to at least mention one project in a little bit of technical depth to give you some more sense of how we're going about things, how we're discovering things. And this is related to direct write 3D printing, where there's a lot of activity of this here at Beckman and across campus. And so let's jump in there. So this is a case where extrusion of a complex fluid has been useful. This is the video that I showed before. These are some structures that were made using this process. And the first question to ask maybe is, what's the rheology that we would want for a, quote, good printing ink? And because we think about the world in terms of these different phenomena, we're a bit abstract at the beginning. We say, first, we definitely want a yield stress. So here's one of the pictures I used to indicate that property. And it surprised us. Nobody had ever really thought about one of those other key phenomena, which is the extensional thickening. This is the thing making the magic smoke work. It's what's used extensively in polymer processing to make fibers and thin films. But nobody had really explored that, in part because these materials that are yield stress fluids, there's a lot of papers in literature that claim they're not extensional thickening, as if that's a good thing, because then all the math is easier. So motivated by mathematical simplicity, people were ignoring the fact that this other complexity could exist if you were to formulate it that way. Well, we weren't afraid to formulate things to be a little more complicated. And so we did it. And we asked, can extensibility help to make this process any better? And how do we achieve that? So this was really led by RF on the rheology side here. And these are pictures showing each of these properties. The lower row, a little small maybe, is demonstrating that these fluids have a yield stress. They hold their shape. They don't form a smooth puddle. They have these cusps. Even surface tension isn't big enough to smooth out and round out these shapes. And then in extension, we stretch them out. And here's how stretchy each one of these materials can be. The one on the left is called bentonite. It's a clay suspension. And it doesn't stretch very far. It breaks up right after this image was taken here. And here's a real printing resin, not for extrusion-based printing, actually for screen printing. And it has a yield stress. And whatever company is using this has a material that has a yield stress and is extensible, even though the academic literature was totally neglecting it with their model materials. And just to demonstrate, everybody knows these materials exist. We have bubble gum. Bubble gum has a yield stress. It's super stretchy. It has both of these things. And it's like staring us in the face. So these are the two properties we were exploring. We had this concept, this architecture concept of how to make it. This is an emulsion of silicone oil and water. I mentioned making mayonnaise. It's kind of like that, but it's silicone oil, so you don't want to eat it. But not just that, we put in a polymeric component. This is polyvinyl alcohol, molecular weight of around 100,000, not super high, not millions of molecular weight. But we also put in this ionic contribution that makes these polymers cross-link to each other, but not permanently like a rubber. They're transient cross-links. And so the chemistry attaches these, but it also lets go over some time scale. That's on the order of a second or so for this particular system. This too is staring you in the face if you know where to look. This is PVA and borax. It's like all over scientific demonstrations of complex fluids. So part of this is trying to show the community like this is obvious if you know where to look and you start making these things. So that's what we formulated and it worked. We can get a yield stress. We can get a lot of stretchiness. And that was the first effort to really push the academic community to start thinking about this other dimension and to stretch their paradigm, if you will, of yield stress fluids. We took that learning and we applied it to the 3D printing. I'll jump over this just to say there's a range of materials that have a yield stress. And I wanted to get a couple slides in here to show you what our experiments tend to look like. We measure these properties a lot. We measure them with things called rheometers. 3 of them are shown in pictures here. Who in this room has used a rheometer before? Or expanding that, given a material to somebody else to test on a rheometer? Or expanding that, heard the term rheometer or rheology before? Okay, so here's what it looks like in the lab. These happen to be sitting in my lab, which is in mechanical engineering laboratory. And they do different things in different ways. They have different strengths and weaknesses, but we'll often test things either in shear flow, simplify the velocity field, or in extensional flow. I have one video of doing the extension test that should play here. This is a gel-like material, kind of like the Allo-Gel. And you see, it doesn't take much to get that to break. It's not very stretchy. But this is what the data looks like. We can measure a lot of complicated properties. We can input oscillations, all sorts of things. So if that's of interest to you, please connect with folks in the group and we can work together to measure rheology of your complex fluid. We looked at the rheology across these more colloquially available materials like whipped frosting and Nutella. Here's the Mystic Smoke. Look at how much extension you get just by putting that onto the surface. Laffy Taffy, Hubba Bubba. We need to switch to a different device when things get really stretchy. So another device we have is to not just stretch with linear motion this way, but to stretch across 2 counter-rotating drums. You have a feel for what bubblegum stretchiness feels like. And here's a bubblegum sample just at room temperature rather than elevated mouth temperature being stretched. It breaks a little sooner when it's at that colder room temperature compared to elevated temperature because of kind of this waxy crystalline component that's in there that melts at higher temperature. And there we go, and then it breaks. And we can measure, of course, the mechanical properties of this. From all of the data we get, we can try to lump that into a couple simple metrics. For example, what is the yield stress? What's the strength required to get the material flowing? And how extensional is it, which we've this high dimensional data set we've collapsed into this very simple metric, which is what's the apparent strain at which it breaks. So we've dramatically simplified, and in doing so, we can make something here called in the field an Ashby style diagram, named after Mike Ashby, who popularized the idea of co-plotting 2 different material properties onto the same 2-dimensional space to see what the trade-offs are. So for example, here we see, at least among these materials, to get a very high extensional strain to break, that only seems to occur for very high yield stress. Here's a bubble gum and a Laffy Taffy that are doing that. All of the colored symbols are all of the academically studied materials. which don't stretch very much. That's basically what we're showing. Even Nutella stretches more than any academically studied material here. There's clearly like a missing gap in what's in the public academic literature and what really matters. You know, if you're a magician or you like sweets or you want to print protective gloves. Okay, so in seeing that, the scientific question is, can we actually make something from the molecular or microstructural design route that can help fill in this space, but serves as a model material, so we can at least study and imitate some of these properties? And the answer is yes. And so we did that in two ways. I've shown you one of those materials, which is that PVA borax emulsion, and then we've done it again for the 3D printing. So here's that PVA borax emulsion. It's very stretchy. We can change a couple things about the formulation. Let me place our work here too. We are not synthetic chemists. We're like the cooks in the kitchen that are combining ingredients. We work with people like Jeff Moore and other folks in chemistry who are making new stuff. And then we like to think about how the mechanical properties result from it. But we can make things at this level of synthesizing, of creating structure. Like there are lots of cool fluid mechanics physics associated with the drop size distribution that you get to make this emulsion, for example. So where do those land on the Ashby chart? They land up here. So we're able to get close to the bubble gum and the taffy in between the Mystic Smoke. It doesn't really violate this kind of trend that we tended to see here, but we at least got something that's more of a model material to be studied. We pushed ourselves farther because of the 3D printing, and we ended up populating this part of the space, which was really cool with a different design route. This was great because we found a way to get approximately the same yield stress, but change only along this other dimension. And this is great for science, right? We want partial derivatives, not complicated, changing two things at the same time. And so that's what we ended up studying and using for the 3D printing. Here's all of those, covering the whole range anyway, of those samples. We're subjecting each of these to uniaxial extension. You'll see that as we increase the molecular weights of the polymer additive, polyethylene oxide is what we have primarily in the water phase that's in here. It gets more and more stretchy. It may be difficult to see the thin filament here, but the video stops when the filament breaks. So at least from the final state, you get a sense of how long the filament stretched. And this was actually really useful for 3D printing. In the baseline case, we can print a line at a slow speed. And if we add the polymer, we can also print a line at a slow speed. But if we want to go fast, this line starts breaking up into droplets. And you're maybe not surprised now that being extensible actually helps you not break into droplets because it's stretchy. And so we can map out what that print speed accessibility range is as a function of, for example, the molecular weight of our additive. This is a multi-dimension space that goes outside of this projection. You can also change the loading of the PEO. You can change the emulsion structure and the volume ratio of those things as well. But within this space, we know where we can print, and we can print fast and small, turns out. And so here's a demonstration of that kind of in the design framing. I have this slide here too. I have two pictures on the bottom that shows that just being able to print this is not really enough. So you can print out a structure. It's like decorating a cake. Or if you're a cookie decorator, it's like the outer wall of the sugar cookies you might decorate. But that's pretty weak, like you just easily eat this stuff. If you really want to make something useful, you need some chemical transformation to solidify. If you don't solidify and you apply a weight on it, you ruin hours of printing time in a snap. But if you're able to transform it in a clever way, here, this is work with Ralph Nuzzo in chemistry. We made these into elastomeric structures. They can deform incredibly and still recover all the way back on their own. And so you need the chemistry, of course, to make this happen, to get the mechanical properties that you want. So with this one particular deep dive of a project, I hope you've seen some of our thinking, both at the continuum level in terms of properties. I'll just point out, we were not relying on mathematical equations to optimize what happened. Why? Because there were no mathematical equations that predicted both the yield stress and the extensibility. And so we would have been stuck in some local optimum, but we would have never found this other, probably still local optimum, but we never would have gotten out of that groove if we only trusted the equations. We're now developing new equations that can describe these properties, of course, because we know that it exists. At the material level, we're also thinking about how to get those properties, but we're not synthesizing molecules, at least in this particular example. So that's one of the examples that we pulled into that review that was recently published with Chai, as I've mentioned. Things that we pointed out in that review article is that if you, back to the putties, because I passed them around, any one of those materials to measure the viscoelasticity, this is not just a single number. This is like the shape of a function, and you can push and pull on these in so many different ways. And so this is one way to probe that viscoelasticity, which is to input oscillatory deformation, change the frequency, and ask how much of that stress that's generated is being stored as elastic energy, that's the solid symbols, or being dissipated as lost energy, that's the open symbols. And the relative storage and loss depends on frequency. You can try to fit a spline to these curves, all sorts of ways to fit it. If you can find a way to reduce it to the most important metrics, then you can put it on something like those Ashby diagrams. And that's not obvious what to choose, but here are some choices in terms of a relaxation time and some nominal modulus to show where those putties fall across this range. Here I'm showing 6 of them. And then this is the PVA borax, but not in an emulsion, showing what range can be covered. And so things like this, these material property charts have been used extensively in material science, but really just for solid materials, never for viscoelastic things, in part because it's hard to decide how to simplify these metrics to just 2 or 3 measures. We also have started pulling things together in a little bit different way than they're organized in the scientific literature. So this is thinking from molecular scale physics, whether you're a polymer or a colloidal suspension, an entangled polymer melt, an emulsified droplet, whatever your structure happens to be, there are some guiding equations that might help you understand where a relaxation time comes from. This is the time for the stress to relax. The way that the most papers are organized, the way that most textbooks are even organized, the textbook that gets closest to this will have an individual chapter dedicated to each one of these rows and never really look at it from a design perspective, which is to compare across all of these things. And that's what we're trying to pull together here. And as soon as you do that, you start seeing these really interesting trends. It's kind of like comparing a dozen different design strategies to achieve some objective, and you start seeing where the pros and cons are. One of the trends that you see, if you're mathematically inclined, you can start looking for where the length scale appears in each of these. So a polymer coil, you can write out a complicated equation that relates to intrinsic viscosity and molecular weight, et cetera, et cetera. But at the end of the day, physically what matters most is the size of the molecule, the radius of gyration, and the time scale will always scale like the cube of that radius of gyration. Where it comes from is related to all of those other parameters. But if you see the length scale cube show up here, you also see that in almost everything else. Spherical suspensions, A cubed. Rod-like particles, L cubed. Entangled polymer melts, molecular weight cubed, although there's a correction to make it more precise, 3.4. What you see too is where things violate the rule, like those emulsified droplets, the mayonnaise or your salad dressing before it gets too crowded. These are not thermally diffusing. This is coming from surface tension. You see a different sensitivity to the length scale. And you start seeing these interesting trade-offs of how to really achieve these properties. So about everything can be useful if you know where to look. And so let me summarize where we've been. Thanks for being on this journey to learn a little bit about what I even mean by these different ways to be non-Newtonian, surveys of ways to be useful. Some summarizing remarks. We've been able to show every one of these phenomena can be useful and creative. I think there are a lot of applications we haven't even thought of yet because, again, this is not part of our undergraduate curriculum to train, for example, mechanical engineers to design with both fluids and solids and these things that are in between. It's just at the graduate level, it's a smaller space of folks trained that way. We talked about organizing principles to help think about this like design. There's often a conflict between the design freedom that you want to have and the realism of actually being able to make something. And that gives rise to a lot of great conversations with people who are in material science or in chemistry about what can actually be made to achieve the properties you want. Talk about these Ashby plots. And I didn't mention this, but that linear viscoelastic time ends up being a surrogate for 2 of these other phenomena, which ends up being interesting in terms of the constraints of your design. If you change that time scale, which is this orange Venn diagram section, you end up affecting N1 and ET sometimes. And the decoupling of that is a question for future work, which is mentioned here. I don't want to read through all of these in light of time, but I invite you, if you're really an expert and interested, you can dig into these details. But maybe let me pull out a couple things. We've really realized that having a data repository for all these material properties would be pretty useful, but it's challenging. Why? Because so many companies that measure their own properties just keep that internal, and there's not much of an incentive for them to make it public because then it gives them a competitive advantage. So it just shines a light on the weird structures we have of our science and engineering right now as a species, but it's really weird to move forward without having more of that shared information. And maybe a comment on this design-driven organization. We're sort of flipping around how the information is organized. Do I start with a particular system I care about, I know I'm working with a polymer and I keep going forward, or am I open to the possibility of lots of different potential ways to make these materials? So I'll close again by thanking Beckman, which has been a great place on campus. You all know this already, but it's great. Thanks for your time to hang out with me and have some free lunch. And I'll just acknowledge a few other collaborators, many people at UIUC, specific folks to the Beckman. Some of them are included here, a couple of students who were highlighted. I mentioned Yilin and Chai, who I think are both in the audience. Actually, yeah, the sabbatical support to go to ETH in Zurich, which Nadia mentioned, was really great. And if you'll allow me, I'll just say, it's great to be alive at a time when tenure exists, when sabbaticals exist, because I think it's a real way to significantly advance ourselves and rise above the day-to-day stuff that occupies ourselves. And a lot of this work was influenced by having some space to do that with Jan Vermont, who hosted me at ETH. So thank you again for your time, and I'll leave it there for any discussion.
Thank you for a fantastic talk. Questions?
Yes. All right. Hi, my name is Kate Wallace. I am the manager of my McCraskey Suite in the basement. I have kind of a funny question to ask you, but it's some of your talking points.
Okay.
So, you know, in the beginning, you talked about the silly putty and how it's a liquid because it fits the shape of the container it's sitting in. What are your thoughts on cats being like a liquid? They fit into the shape of their container.
That's a great question. Is this leading to a microscopy suite question or just a cat question? Okay. I'd love to comment on that. There's a great paper that's actually been written about this very question. That starts with many beautiful beam photos, but they pull photos together of cats taking the shape of their container, and not only taking the shape of their container, but also demonstrating viscoelastic bouncing, you know, where they like land on their feet, but then they spring above, and that's like the bouncing putty, and even the normal stress difference of winding around things. And it's a lovely little playful thing that was written on the rheology of cats, would be the key words, I think, for you to find that. Yeah. It happened to win one of these prizes called the Ig Nobel Prize. I don't know if you're familiar with that. It's written as if the author knew that that was going to happen, or was like targeting that, and it was well received. So yeah, fun question.
Very nice talk. Thank you very
Thanks
much.
for
So you mentioned that the mathematical model, the continuum level, does not really exist. You have to both the shear response and the extensibility.
For the yield stress fluids that are extensible, it does for traditional polymeric systems, for sure. You know, traditional polymer processing, people worked very hard for decades to get to those equations, and we have them now. If it's homopolymer, linear polymer melts, very, very good equations now, but not for this other class of materials where you have a yield stress. Sorry, I didn't mean to interrupt. I just want to clarify.
You mentioned that you guys have been working on extending the theory in that direction.
Yeah.
Shed some light as to what direction you're going?
Yeah, so what's the flavor of what it involves? It involves really continuum level modeling rather than like, it's not Brownian dynamics or molecular dynamics, because the value we find is in the continuum level model that we can put into the conservation momentum equation that I showed earlier, right? That's where the real value is, to make a real prediction of what's going to happen in flow. So at that continuum level, it's tensorial equations, and it ends up combining certain features of what the yield stress 3D tensorial models look like, and features from this traditional polymer processing world, what they look like, that end up, I know that you're an expert in this area, and so it ends up using things like upper convective time derivatives for the stress, like Oldroyd B models, upper convective Maxwell models like that, combined with things that end up looking like a yield stress, but not the mathematical trick there, if you'll allow me to go one step deeper, because this is fun. With the yield stress, you know, like the concept is like before or below a yield stress, no flow. Above this, it's a discontinuous change, and that's a nightmare for computations. And there are ways to regularize that. And so that's an important trick going into this, is to not have a discontinuous criteria for the yield stress, but to find a clever way to regularize it so it still acts like a yield stress, but you still see a finite viscosity below that threshold.
So with rheology, we talk about like stress, which is, you know, our inputted force, and then strain, which is our deformation from that force, or vice versa, right? Mm-hmm. But you know, we typically look at this pretty simply. Is there a better like variable to kind of hit these like extensibility or like,
Mhm.
or a more like overarching approach? Because typically, at least what I've done is you take shear rheology to look at one, and then maybe you do tensile or you kind of hop around. Is there something that maybe could be like a blanket test for each of these?
A blanket test, like a single test that tells you about all of those key phenomena.
Or some of them.
Let me-
I mean, like, it just seems like I'll blame myself, but.
Yeah, I'm gonna go back to,
simplify.
yeah. I'm gonna go to this slide, or no, actually, there's a better slide. Give me a moment. I'm gonna go to the slide that shows the 4 phenomena and then how we measure those properties, which Chai helped me put together here. So I think this is a good talking point. So this is an incomplete list of 4 ways to be complicated, an incomplete list of 4 ways to make measurements. These are just schematics of properties that you might measure. All of them involve concepts of stress, strain, and strain rate. I don't think we could ever get around that. But maybe what we can get around is that, all of these are very simple deformation fields. They're either, this is getting to your question, I think, either simple shear, like sliding plates and a fluid in between, or uniaxial extension, very simple tests. And that paradigm allowed incredible progress to be made with complicated materials because you isolate different effects this way, right? The extensional thing is a different phenomenological thing than the shear thinning, for example. I feel like what you're suggesting is like, wouldn't it be cool? Well, maybe this is just my bias. I really think we can get around one of those paradigms, which is to use more complicated flow fields to probe some of these things, which the trade-off though, or the double-edged sword is that now it's all combined and you're not cleanly separating. And so you need very credible models to be able to interpret what's happening. And that's going to be the Achilles heel. If you have a material that you don't really know if the model works or not, then you're going to get garbage out of that analysis. But I think that there are some methods to allow some of that. So I don't know if that's getting to your question though, like combining this or doing it a little differently than we traditionally have. Yeah.
I have 2 questions. Let's do the first important one first. So when you test, does somebody chew it first?
Yeah, you have 2 options. Either they chew it for 10 to 20 minutes to get all the dissolvable sugars or sugar-like things out so it's consistent. Or you can actually do that with pliers or something mechanical in water. It does the same thing.
Yeah. The other one is, as a biologist, I'm thinking about materials that start out soft and become hard, like insect cuticle. At that time when it is soft and doing all these kinds of things, and then being under a stress or shear force or whatever, which in the end results in the final product, which has to be perfect. I mean, have you ever thought about that? Like how to test that? I mean, it's such a fleeting moment, but it's so.
I'd love to think more about that. I think the challenge you're pointing to, the fleeting moment, is that it's mutating or transforming so rapidly, it's hard to really know what the properties are in that time scale. Like some of these tests, it's like apply a strain and see how the stress relaxes in time. But if things are changing over a time that's this short, you're never going to see any of this information, even though it would do that if you could freeze it there. The same challenge exists in engineering applications. And so there may be some interesting intellectual overlap there of like more rapid ways to get at this information than having to wait and do all of the battery of tests. Yeah, that's interesting. How small is the material? What's the scale? I guess you said insects, so I'm guessing at least millimetric or lower, or so, or at most millimetric. Okay.
Nothing done on.
Yeah.
But then maybe using some of the modeling, if I know what it is. But I would start out as and then do some modeling. Yeah, and then
trust the credibility of the model to help you infer what might be going on. Yeah. Thanks for the question.
Hi, great talk. I really enjoyed it. So you mentioned at the end the concept of idea of like data repository and also kind of the collection of all the mathematical models of different systems. So I'm curious, like let's say if there is such a repository existing and we really had a more complete set of those models. So how would that be kind of improving our current status of like inverse engineering problems? Let's say we have a very arbitrary system we want to design. We know, roughly speaking, like the moduli with respect to like shear rate, time scale, etc. We know what we want, but how do we use those knowledge to inverse engineer to achieve our like goal?
Yeah, the most impactful, early impactful thing that would enable would be material selection at a level that's already being done with solids materials. You know, like if you're designing, I don't know, a drone, you're like, I need this material to be light, low density, but I also need to be this strong. You see what your options are by having a material selection database like that. And you don't even know what's out there right now, right? You can like comb the scientific literature, you find a couple things, but it's like only seeing a couple places on the map. You have no idea what might also exist. And that's what it would really enable, is the material selection, which is a common step in the design process, at least for engineers building real stuff. You select the materials to be used, and that's what it would enable, first and foremost. Yeah, especially if you already know what you're looking for. And I think that was your problem statement. That's not obvious, but if you already know what you're looking for, it's the material selection that would be enabled. Yeah, good question.
I have a quick question about these tests. When you're doing these tests, especially for breaking points, how much is the geometry of material matter at that point?
Oh, this is great. Oh, you're good. You got a good experimentalist here heading the Beckman, because the test that I showed, what I'm showing here is as if these are material properties independent of the size and the shape. And so we call those intensive properties. But what I showed in terms of the strain to break, it's an extensive property. You know, there's no way to guarantee that things would be different if you had, wouldn't be different, larger or smaller, especially because of other effects like surface tension, operating small scale. So that's an extensive thing. Yeah, the defects. Yeah, that's right. You go on very small scales. So it's very much an extensive property. Still useful, but extensive. We explored the sensitivity to that. You know, like if we change the initial aspect ratio, it wasn't that sensitive.
Okay.
It also depends on the rate. It wasn't sensitive enough to make us worried about the insight we were able to get. So we just did it, and it guided our design and our insight there.
Okay, oh, one last question.
Yes. Interesting. Yeah.
Things that you can imagine that could be part of our thinking away from a system like that to change the electric properties. That might have done something.
Yeah, like you're talking about human health, sort of stuff, those sort of materials. Oh yeah.
Change those properties.
What a playground that would be to do things like that. I mean, well, let's chat afterwards. That'd be really fun. I'll just let the question close everything out. I love the question. And I don't think I've seen people doing things like that before, but maybe you are.
Okay, that's a great question. And don't forget the photo in the Atrium 315 donuts, be there. And let's thank you again for
thank you.
That's great.